lot to cover this week as we talk about effect size and more complicated designs in MANOVA. So when we think about ANOVA, a univariate ANOVA, there's several different possible effect sizes we can think about. And you'll often see Cohen's d for comparing means, but you'll also often see eta squared and omega squared, or partial eta squared and partial omega squared. And these are a direct corollary to R squared or adjusted R squared in regression. They're just computed using ANOVA-based statistics rather than regression-based, but they're pretty much the same thing. And I think that they're exactly the same. So eta squared is the ratio of the sums of squares between to sums of squares total. And so this is a ratio of the essentially the proportion of the total sums of variation and sums of squares attributable to the sums of squares between, or the sums of squares of the effect. So it's the proportion of variability in our dependent variable attributable to our independent variable. Because eta squared is actually biased, it's upwardly biased, we can adjust for this bias with omega squared. This is the same thing as using adjusted R squared. So there's a correction that we use to try to mitigate the bias a bit. And this is shown to be a slightly more accurate representation of effect size. So in MANOVA, it turns out that all this hard work we've already put in makes finding an effect size relatively easy. So remember, in the univariate case, eta squared is the variance of the ratio of the variance of the group effect to the variance of the total effect. It's the proportion of total variance accounted for by the grouping variable. So let's quickly establish a new definition, and you've probably seen this in lecture. So the determinant of a covariance matrix can be thought of as the generalized variance of the covariance matrix. So it's a single number that represents the amount of variability in the covariance matrix across the variance is on the diagonal and the covariance is off the diagonal. So do we already have some kind of ratio where the denominator is the total generalized variance that we've seen before? Have we seen something where the denominator is the determinant of a total effect? It turns out we have. We have seen this with Wilks lambda, which is the determinant of the within SSCP matrix to the determinant of the total SSCP matrix. This is pretty close to what we need. The problem is that this is actually the reverse of what we need. So this is the ratio of the within effect. What we want is the ratio of the between effect to the total effect. So we could redo the fraction and just sub in b, or we could do something a little bit simpler. Given that t is just w plus b, we can actually just take 1 minus lambda, and that will give us our eta squared. So this is the same thing as just the ratio of b to t. 1 minus lambda is our eta squared lambda. So like regular eta squared lambda is a biased effect size. However, we can also map our original lambda onto an omega squared lambda, and we do it like this. So now we're taking 1 minus this correction for our sample size and number of groups. And that's our omega squared lambda, which is unbiased. There isn't actually a default function to get this omega squared, but it's really simple to program one in R because it's just a direct function of the lambda statistic. So we just plug in a lambda, the number of groups, the sample size and number of groups, and that'll give us our omega squared. So let's take a look at an example using the Star Wars data we saw last week. So I'll load up my data and I'll convert my grouping variable to a factor just to make life easier. I'll run my MANOVA. So I'm also going to count the number of observations and the number of groups. So that's going to be 267 and 3. So now I just have to pull out my lambda. I could, of course, just write it. We see here it's 0.3348, but you can get it out of the summary object as shown here by creating the summary object, extracting the statistics, and indexing the grouping variable name, and then Wilks. That just gives you the Wilks lambda from the output object, the summary object. And now I can just take 1 minus that to get my eta squared, and I can plug in that, the lambda, the n I computed, and the g I computed into the function I wrote before for omega squared lambda to get my omega squared. And so notice that the omega squared is a little bit smaller than the eta squared, which it always will be because there's the correction for bias. So the way we can interpret this is that the film participants saw explained approximately 66% of the generalized variance in entertainment, writing, and action simultaneously. And I'm basing this on omega squared as defined by Stein and Ellis, 2009. And so one thing to notice is that I specified the version of omega squared that I'm using. And this is because there are actually lots of different ways of thinking about effect size in MANOVA. And there isn't really like a universally accepted most popular one at this point. This is based on a paper that David shared. I believe he shared it with you as well. And this is just a very straightforward, nice, easy to interpret version, which is why we like it. But there are some other versions. So even Stein and Ellis, they defined a slight variation that adjusts for sample size. And that's sort of just the tip of the iceberg. There's also some automatic functions in the Heplots package for the eta squared test statistic, not the omega squared, but the eta squared. And these are each based on one of the 4 MANOVA statistics that we've seen, Wilks, Pillai, Hotelling-Lawley, and Roy. And so actually even the lambda one, even Wilks, is different from the one we saw. They're all more complex formulas. They generally have some kind of adjustment for the number of groups or the number of dependent variables. And so because there's so many different versions of these effect sizes kind of floating around, it's important to be clear about which one you're using. So if you're going to use one of the ones from this automatic function, you should be clear that that's what you're doing. There's some papers that are cited in the documentation here that you can always use as a citation in practice. For the homework, you can use whatever effect size you want. Just make sure you're telling me which one you use and you're clear about it. Don't just write the effect size without including some kind of reference to what you're doing. And if you were to use one of these in practice, you should cite probably one of the papers in the help page. And so you could click the link there. And there are a couple papers that discuss the types of effect size they're using. The help page also has the formulas that define them, but then there's some references to papers as well. So here is an example of the eta squared based on Pillai's trace from this package. And you can see it's totally different. Before we got 0.66 and this is 0.40. It's capturing something, it's a different representation of the effect. It's adjusting for something else in a different way. It's probably not as easy to directly interpret. I'm not sure, I haven't read through the papers in enough detail to understand exactly what the justifications for the different effect sizes are, or the exact way, the reason they think that they should be interpreted in the same way. But so it's just either way, it's just important to be clear about which version you're using, just so people know what they can compare it to. So that's effect size, which we'll talk a little bit more as we talk about two-way ANOVA here, or two-way MANOVA. So in two-way MANOVA, we don't just have one grouping variable, we have 2 grouping variables that are crossed. And this is the same thing as in two-way ANOVA. So that means that each observation is one of several possible combinations of groups or conditions or assignments. So we can think of this like we call this a 2x2 cross design, and we can think of this like a 2x2 contingency table. So here you see my rows are one grouping variable, which I'm writing as G1 and G2, and then my columns are another grouping variable, B1 and B2. And so there's 4 different means. There's the mean for the combination of G1 and B1, G1 and B2, G2 and B1, and G2 and B2. So really, even though I have 2 different grouping variables, I have 4 total groups, 2 times 2. So we can write, or we can sort of decompose our means the way we have been with our sums of squares by thinking of them like this, where we have 3 different indexes, L indexes from 1 to G for the G grouping variable, K indexes 1 to B for the B grouping variable. So in the 2x2 design, these would just be 1 and 2, but they can be any number for depending on how many groups are associated with each grouping variable. And then R is the total sample size. So it goes 1 to the total sample size. So we would decompose each observation as the grand mean, subtracted by the mean of group L subtracted from the grand mean, plus the mean of group K subtracted from the grand mean, plus the mean of group LK subtracted from the mean of group L subtracted from the mean of group K, plus the grand means. That's the interaction. And then finally, there's some residual error there at the end. So this is what I just said. This is just a written English version of what we just saw on the previous page. So it's a little bit easier to interpret. So taking the sums of squares of these error components across all observations provides a framework for sums of squares in two-way ANOVA. Dividing by the degrees of freedom for each component gets us our F ratio, and then we can test different hypotheses comparing sums of squares to sums of squares residual, or sums of squares within, or in this case mean square residual, mean square within. So here you see we have each of our factors and the degrees of freedom. So you remember, you divide the sums of squares by the degrees of freedom to get the mean squared, and the ratio of the mean squares is how you get your F statistic, and this is for regular ANOVA. So all of this generalizes, just as we've learned, to multivariate world, or MANOVA world. So we're replacing all of our single variables, our x and x bar. We're just bolding them, which represent that they're now vectors and mean vectors instead of single variables. Instead of sums of squares, we have sums of squares and cross products. And instead of mean square ratios, we have Wilks lambda, where we test the ratios of the determinants as the sums of squares of the residual. So the sums of squares within divided by the sums of squares of the hypothesis plus the sums of squares of the residual. And these are SSCPs, sums of squares and cross products. So the SSCP hypothesis is the SSCP matrix for one of our factors or their interaction. So here's the table for the multivariate version. So you see we have factor 1, factor 2, and their interaction. And they have degrees of freedom for each. So this is just, this is written, these are exactly the same as the univariate case, except we're using the vectors and we're multiplying them by their transpose instead of squaring them. And then we have error at the bottom, which is the within. So the thing we have to think about now is what's the order that we're going to do our tests in two-way MANOVA. So what's the first hypothesis we're going to test by plugging something into our SSCP hypothesis? Which SSCP are we going to plug into SSCP hypothesis first? So there are three possibilities. We could do factor 1, factor 2, or the interaction. And so you can think about what we do in regular ANOVA 2, where we test one of the factors or we test the interaction first. And the answer is we test the interaction first. The next thing to think about is if the interaction is significant, what do we do from there? Do we proceed to interpret the main effect results? And when we test the interaction first, we typically and get a significant result, we typically don't then proceed to test the main effects. The reason being, if the interaction is significant, it means the effect of factor 1 is different depending on the level of factor 2 and vice versa. So we really have, in the 2x2 case, 4 different groups as opposed to two sets of 2 different groups. So we only directly interpret the main effects in a two-way model if the interaction is non-significant. So let's look at an example. So in this example, we're going to imagine, this is again simulated data. So we're going to imagine this data was collected on 676 participants to study the effects of diet and exercise on well-being and sleep quality. So each participant was assigned to either a control condition where they did what they would normally do, or a treatment where they either followed a special diet, a special exercise, or both. And so in our two-way MANOVA, we want to check whether there were simultaneous differences between each group on well-being and sleep, and whether the differences in one treatment were conditional on the other treatment, and vice versa. So we can, again, look at this as our a 2x2 contingency table. So we have our diet condition here are the rows, our exercise condition of the columns, and we have slightly different sample sizes for each one. So we're going to take a look at our data here and just see what get a sense of what it looks like. And then we're going to run our two-way MANOVA. This is just like we would run our regular MANOVA, except now we have the interaction between two different grouping variables instead of one. And so we get our output here. And so we have 3 lines in this table. So the line for the interaction and then the line for each main effect. But here our interaction is significant. So we're really only going to interpret the significance of the interaction. The effect of diet on well-being and sleep quality is different depending on which group of exercise one is in, or you could write that vice versa. And so there's my statistics. We could also get a more detailed output with the summary MANOVA call, where this is the MANOVA from the car package. And so this is a really long output. I need to share a slightly different screen to show you. So let me show you that. So I already pulled it up. So here is that more detailed output. So you see you get all 3 statistics for each term, including the intercept. So we don't really worry about the intercept here. So first we get at the top, we get the error. So this is the SS error or SS residual. Then we get for factor 1, which is diet, factor 2, which is exercise. So you see we get the hypothesis, sums of squares, as well as the 4 tests, and then for the interaction at the bottom. So we interpret this bottom one first in this more detailed version of the output. So we can also think about effect size. So for the interaction, we have 4 different groups. So we're going to plug in 4 for G, and then our N is our total sample size. So we get our omega squared of 0.07. So we can also, if the interaction is not significant, we may want to get the effect associated with each main effect. This is a little bit difficult to interpret because of the interaction, but if there was a non-significant interaction, we can interpret these as well. And so you can also sum them, even when the interaction is significant, you can sum the main effects with the interaction or interactions to get a total effect across all grouping variables. So the interpretation here is that in total, differences between control and treatment in diet and exercise explain 48% of generalized variance between in well-being and sleep simultaneously. And so just remember, this is simulated data. It probably isn't this much of the variance. Let's actually explain this is probably an overestimate of what this effect would be in a real study.